Welcome back, everyone, for the fourth lecture of for our Calc 3 class. What we're going to be looking at is, now that we've seen some examples of points and functions in polar coordinates, we want to start extending this to, well, how can we use calculus in polar coordinates? And an extremely important topic is how to find area in polar coordinates. So we remember from Calc 1 and 2 that if you have some curve, y, say y equals f of x, right? If we want to look at this function from, say, the x interval a to b, well, then we can talk about area bounded by lines extending from x equals a and x equals b, and then bounded between your curve and the x-axis. We know that the area here can be found by just simply taking the integral from a to b of our function, right? And so what we want to do now is try this in polar. Right, when we're looking in polar coordinates, we could have a chunk of a function doing something like this, maybe over here. And now what we want to look at is the area bounded between the lines, some starting theta and some ending theta, say alpha and beta, and between these lines and our curve. So say here this curve is r equals f of theta. And we want to know now what this area is. And that's what we're going to take a look at deriving today. We're going to see if we can derive the formula for computing area bounded between two theta rays and a curve. So let's take a look here. So when we're trying to calculate area, a really common trick is to subdivide our region. And so say here, we have our region between theta equals alpha and theta equals beta out here, right? Usually what we try to do is start with an approximation by giving some equal partition into a finite number of subintervals. So if we want, like, let's get an equal partition here. And to say, let's call theta 0 to be alpha. And then we'll partition this by the rays theta 1, theta 2, etc. We'll go all the way up to theta n, which will be beta. Okay, and so if we look at this partition, right, we get theta equals theta 1, theta 2, etc., etc. And we subdivide this all the way up to, so like here's theta 1, theta 2. You keep going. This ray up here would be theta n minus 1, and then beta would just be theta n, right? And so now what we want to do is get an approximation of this area by looking if we can get the area of individual sectors here. These are called sectors. So let's see if we can come up with a formula for the area of a sector. Let's look, so for the area of the ith sector equals what? Well, let's take a look here. Let's just go to the general case for a second. If we have a circle of radius r, and we're looking at a sector spanned by some angle, so I won't call this theta here, but we have some angle in here, and we want the area of this sector. Well, we need to use the area of the entire circle. The area of the circle is given by pi r squared, right? The area of the sector, so maybe I'll call this area of the circle, a sub c, and then area of the sector is given by the angle of this chunk here is going to be theta, but it's 2 pi over theta because it's a fraction of the entire circle, right? Sorry, excuse me. Our theta is a fraction of the entire circle, right? The entire circle's angle is 2 pi, right? And we want this theta, which is just a fraction of that 2 pi, right? And so we want to take this and multiply it by the area of the total circle. And what we're doing now is we're getting a fraction of the area. And that's what this fraction theta over 2 pi is doing, right? And so that means the area for a sector is the pi's cancel, and we get 1/2 theta r squared. So this is in general how you find the area for a fraction of a circle. It's what we call this little sector here. So now if we're looking back to this is some curve, r equals f of theta, and we've split this into I sectors, or n sectors, excuse me. If we split this into n sectors, let's say this one here is the ith sector. Well, then what is the area of this going to be? I'll call it a sub I. The area of the ith sector, well, based on this formula, is going to be 1/2. And now we want this angle in here, which is when we've subdivided this based on a partition, this tiny change in theta is what we call delta theta. It's a very small change in theta. And then times r squared. But we know that r is not necessarily fixed. When it's a circle, r is fixed. But in general, some function in polar coordinates, r is not fixed. So we need to take r as f of theta I squared. We want f of theta I, right? We want the ith. We want the length of the ith sector. And as we vary, as we go to the next sector, say, right, we would have something like this, something like this. You can kind of split it up so it looks like an approximation again. Right, when we go to the next sector, this radius can be different, right? And so this is our formula for the area of the ith sector. Okay, and now we have area for the ith sector. So what's an approximation for the area, right? An approximation is to sum all of these up, and we'll call this a sub n. So I want to say total area is approximately equal to a sub n, which is the sum from I equals 1 to n of the area of these sectors, of each sector, right? Which is the sum from I equals 1 to n of 1/2 delta theta f of theta I squared. Okay, and now to get an approximation to become exact, we need to take the limit as n goes to infinity. So now a is going to be exactly the limit as n goes to infinity of a sub n, right? And this is the limit as n goes to infinity, sum I equals 1 to n, 1/2 delta theta, f of theta I squared. Taking the limit, this sum turns into an integral, and what we get is 1/2 the integral from alpha to beta. Remember, alpha and beta were what we were starting and finishing our theta values at. And so it's 1/2, and we get f of theta squared, f of theta squared d theta. And now we've derived a formula for calculating area under, excuse me, under a polar curve. So let's kind of recall what we've learned with the theorem here. Let's let r equals f of theta be a continuous function over the interval theta goes from alpha to beta, okay? In general, let's also just kind of restrict that beta minus alpha is between 0 and 2 pi here, okay? Then the area of the region bounded by our function r equals f of theta and the lines theta equals alpha and theta equals beta. The area bounded by these curves is given by a equals 1/2 the integral from alpha to beta. That looks like a row here, sorry. 1/2 integral from alpha to beta, f of theta squared d theta, or if you'd like to write it in a slightly more concise way, this is 1/2 integral from alpha to beta r squared d theta, because we know f of theta is just r. And so here is our formula for being able to compute area under a polar curve. We just look at the function and square it and then plug it directly into the integral. And then you take half the value of the integral, and that's your area. So I want to go through one example all the way, and then I want to go through another example that's just a setup so we can see how to solve these types of problems. All right, so let's do some examples. Here's the first example. Let's find the area of one petal of the rows r equals 3 sine 2 theta. Okay, so we need the rows, or we need the area of one petal of this rose. And so if you remember from our discussion on polar curves, you could either plot points to get an idea of this curve, or you can remember the handful of examples I went through here. So the 2 here tells us that we're going to have 4 petals. That's the number of petals times 2. And 3 tells us kind of the major radius of each petal. So it'll look something like this. Here, where this length is 3, and we have 4 petals, okay? And so the question says, what's the area of just one petal, okay? And so to find the area of one petal, we know what our formula is. It's this 1/2 integral alpha to beta r squared d theta. And what we need, because we have r explicitly given to us, so we simply just plug this in, right? What we need is our bounds. We need to know what are alpha and beta, right? So what are the bounds? Okay. So when finding the bounds, you want to look at how this curve is traced out, right? We start at the origin and we start tracing in this direction. When we start at the origin, we can plug in theta equals 0 to get r equals 0. So that means at the where we're starting at the origin is at theta equals 0. So that means the first ray that we're bounded by here is alpha equals 0, right? When we're starting this here, we want to take the ray corresponding to the first theta value that we have here, right? And as we go around, we see kind of by the same argument that we stop along the line theta equals pi over 2. You kind of trace out one petal, you can see it's bounded completely in the first quadrant here, right? And so that means our bounds are from 0 to pi over 2. So our formula for area is 1/2 integral 0 to pi over 2 of r squared, which is 3 sine 2 theta squared d theta. And now this is an integral that we're well equipped to solve, right? This would be a equals, so let me just copy it really quickly, 0 to pi over 2. It was 9 sine squared 2 theta d theta, which becomes 9/2 integral from 0 to pi over 2 sine squared 2 theta d theta, right? And from here, you can use a trig identity on sine squared, and this becomes 9/4, right? Integral from 0 to pi over 2, 1 minus, it should be cosine of 4 theta d theta, right? Because, so let's remember what trig identity I'm using. I'm using that sine squared of x is equal to 1/2 times 1 minus cosine of 2x. The 1/2 here found its way out front of the integral, so I combined the denominators so that's 9/4. And then here we have 2 theta. So when we use this trig identity, we need to take the 2 theta times 2, which became 4 theta. Okay. And so now we can simplify. We can actually take the integral here. So if we actually take the integral, this becomes theta, and then it looks like it's going to be minus 1/4 sine 4 theta, right? And we're evaluating this from pi over 2, or from 0 to pi over 2. And notice if you plug in pi over 2 and 0 to the sine function, we get 0. So those cancel. The only thing that will not vanish is plugging in pi over 2 to theta directly. And if we do that, our total area becomes 9 pi over 8. And so we've now used this formula in an explicit example to learn that the area of one petal of this function was 9 pi over 8. And so here's an example of just how we can directly use this formula. You just take what the function is, you determine what your bounds should be, and you integrate, and you're good to go. I want to do one more example here. So here will be example 2. But I won't go through the full problem here. It'll just be a setup so we can see how these kinds of problems can be solved. So let's find the area between the cardioid. Let's go with r equals 2 plus 2 sine theta. And the circle r equals 6 sine theta. So we want the area between these two things. So when we graph these, we can graph these. So the cardioid looks something like this. This will just be a sketch of the graph here. Let's fix that. Here's our cardioid. Okay. And then we have the circle r equals 6 sine theta. So it looks something like this here. Once you graph these, we want the area between the cardioid and the circle r equals 6 sine theta. So that's my wording is a little misleading here. Let's say the area outside the cardioid and inside the circle. Okay, outside the cardioid and inside the circle is going to be this region here, right? Because the circle is r equals 6 sine theta, and the cardioid in blue is r equals 2 plus 2 sine theta. And so this is much more clear what I'm asking for this problem, right? It's the area outside of the cardioid, outside of this piece, but inside the circle, which is in red. So we want the area of this piece, okay? And so now we have already is a little more complicated setting. We have two polar curves, and now we want the integral outside of a polar curve and not inside. And how we handle this is we still count the area inside of this innermost polar curve here. We still count that, but we subtract it from the area inside of the larger curve. So here we can say that the area is going to be the integral. So if you'd like, it's going to be the integral 1/2 integral alpha to beta of the outer curve squared minus the integral of the inner curve squared, right? And then like d theta, d theta. What this does is if we start with finding the area of the outer curve, what we're going to get is all this, I'll indicate it in yellow. We're going to get everything, right? If we find this, we'll be getting the area inside the entire circle here. But we don't want all of it. We only want the part that I drew in red. And so what we can do is we can take the integral of the inner. If we took the integral of the inner curve here, that would get us all of this area in blue. And notice the area of the yellow without the blue is just the red part there. So that means we can take the outer curve, the integral of the outer curve, minus the integral of the inner curve to get our area. So let's see what that would look like. So we'll get A equals 1/2 integral from alpha to beta. Now what's the outer curve? It's the circle in this case, right? So it's 6 sine theta squared d theta minus 1/2 the integral from alpha to beta of the inner curve, which was the cardioid. So 2 plus 2 sine theta squared d theta. And so now we have the integral set up. We just need to figure out what our bounds are. So again, what are bounds, right? Well, when we want the integral between, maybe I'll redraw the picture here. Then we have a circle like this. When we want this area that I'm drawing in green here, we would start and stop where these curves meet, right? Meaning we want to start and stop. We want to bound this by their intersection points. And so taking ray from the origin through this point, this should be some theta value. Doing the same thing for the second point should give us another theta value, right? But how do we figure out what these are? Like alpha is what and beta is what? Well, if there is a self-intersection, or if there's an intersection point on the graph, that means they are taking the same values at these points. So what does that mean? It means the functions are equal. So the bounds can be found when the functions are equal. So we have 6 sine theta is equal to 2 plus 2 sine theta. And here's how we find the bounds. Now you just solve for theta, right? So we get that 4 sine theta equals 2. So sine theta equals 1/2. Sine theta equals 1/2. If you remember from the unit circle, this is when theta is pi over 6 and 5 pi over 6. So this angle here is pi over 6. And this angle here is 5 pi over 6. And so we can get now a full expression to be able to solve our solve for area between these two curves. And it's 1/2 integral from pi over 6 to 5 pi over 6. And it was 6 sine theta squared d theta minus 1/2 integral pi over 6 to 5 pi over 6, 2 plus 2 sine theta quantity squared d theta. And now we could work out what the area should be, because these are both integrals that we're equipped to solving. All right, so this is all I wanted to talk about for finding area under polar curves. And in the next video, we'll talk about how we can compute, we'll derive a formula for arc length of polar curves. So I'll talk to you guys in the next video.